Welcome back, everybody. This is AP Chemistry, beginning Unit 9, Section 1. We're taking a look at acid-base equilibrium. Now, this builds off of Unit 8, where we're doing acids and bases and calculations with that. And so this section, or this unit, I should say, is more about the buffers, about what happens when we add in things. So we know how to calculate acids and bases when they're in equilibrium. Now, if we're adding other things in there, there's going to be a shift in the equilibrium that occurs because of an ion that's already involved in the equilibrium. So let's take a look at an example of just a review of what happens when we are just looking at an acid. Now, hydrofluoric is a weak acid in here, okay? A weak acid is, it's not going to dissociate completely in there. So let's take a look at my hydrofluoric, and it's going to dissociate into hydrogen ions and my fluoride ions, okay? And we had a 1 molar solution, and so it's going to lose a certain number of those hydrogens. He's going to gain, and he's going to gain. All right, we know how to do all this. We have the Ka value is supplied for us as 7.2 times 10 to the negative 4. That's going to equal x squared over 1 minus x. And since x is a small value, I can disregard this x right here. So it's basically 7.2 times 10 to the negative 4 equals x squared. And so my x then, if I just take the square root, is a 0.0268. My pH then would be the negative log of that. And so my pH ends up being, in this case, a 1.57, okay? This is something that we already know how to do, all right? From Unit 8, just taking a look at the pH of those things. Now, let's take a look at what happens when we add something in as a buffer, and I'll be explaining what that means in just a moment. So I'm going to leave this right here, we saw that this is a 1.57 pH for just the hydrofluoric, okay? Now, let's add in this sodium fluoride as a buffer, okay? What happens is we end up changing what my major species is all about. My major species is what's floating around in that solution, if you remember. We have the hydrofluoric in there. We have the sodium fluoride that's floating around in there, but they're going to dissociate, aren't they? They're going to dissociate in my hydrogen ions. They're going to dissociate into my fluoride ions from this guy, but it's also going to dissociate into my fluoride ions from the sodium fluoride. And I'm going to get my sodium ions in there, and of course, to get them to dissociate, I need my water. Now, the sodium itself isn't going to do anything, neither is my water. Okay, they are a major species, but they don't actually, in fact, do anything. But we're going to see that this fluoride is going to be absorbing in some of those hydrogens. Okay, it's going to eat it up, if you will, to describe that. So if I chart this out a little bit, I get my hydrofluoric acid is going to be dissociating into the hydrogen ions and the fluoride ions. But remember, there's fluoride ions coming from the sodium fluoride as well. And so I'm starting with my concentration of 1, and I'm going to be losing some of that along the way. Now, my hydrogen ions, I'm going to be getting that. And what I was describing is this buffer is going to be absorbing some of the hydrogens. How much? Well, that's an X as well. Okay, this 1 came from the 1 molar solution here. All right, so if I add this all up and I see my Ka value was a 7.2 times 10 to the negative 4, I see that it equals my X for my hydrogen. I see it's a 1 plus X from these fluorides all over 1 minus X from my hydrofluoric. Now remember, this is a small value of K, so I can eliminate that, and so this ends up being 7.2 times 10 to the negative 4 equals X, because it's just times 1 over 1. Okay, so 7.2 times 10 to the negative 4, that equals X, and so my pH is going to be the negative log of that, 7.2 times 10 to the negative 4, and so I see that my pH ends up being a 3.14. Okay, that's because I added in my sodium fluoride. And I said that that sodium fluoride, those fluoride ions will eat up some of the hydrogens. And what does that do? That raises the pH, because remember, pH is a concentration of hydrogen ions floating around. We would expect this value to be higher because of the sodium fluorides that we added. That, my friends, is the definition of a buffer. Okay, so we're going to be taking a look at some of these things. A pH change or resistance to a change when we add some things in there as well. Okay, a buffered solution is one that's going to resist the pH change as we go. Okay, so let's take a look at another example of what I mean by that. We see that we have the acetic acid. We see this guy a lot. This guy is a weak acid. We know he's going to dissociate into hydrogen ions. Okay, so it's my HC2H3O2 is going to dissociate into hydrogen ions, and my acetate C2H3O2 with a negative. Okay, so we know that it's going to dissociate, but not very much in there. Okay, it's a weak acid. And so now we're going to be, and notice that we started with a 0.50 molar solution of it. But now we're going to be adding in also some of my sodium acetate. Now this is an ionic compound, so what happens when they're ionic? It dissociates completely. Okay, so it's going to be releasing these acetates right here. And what does that acetate do? Well, it's going to eat up some of the hydrogens. Okay, so what we see is that we're going to lose a certain amount of this. He's going to gain, and notice that I've got a 0.5 molar solution here, and so that's a 0.5 molar, but he's going to gain some of these hydrogens. All right, so using my table, we've done this quite a bit. My Ka value ends up being 1.8 times 10 to the negative 5, and that's going to equal my X for my hydrogen, my 0.5 plus X for my acetate, over my 0.5 minus X from the acetic acid. Again, these are going to be small values of X, so I can disregard those. Notice 0.5 over 0.5, so those will cancel each other out. My Ka will actually, or my X I should say, equals the 1.8 times 10 to the negative 5. So my pH is the negative log of that, of 1.8 times 10 to the negative 5. And so I end up with a pH of 4.74. Okay, that's going to be considerably higher than what it was in the first place. So let's look at our major species that we had here. Okay, my major species was my acetate, or my acetic acid, I should say. And I'm going to get my hydrogen ions. Okay, and I'm going to get my acetate ion. Now remember, where that acetate ion came from was my acetic acid, but it was also from my sodium acetate. We don't really consider my sodium as a major species because he doesn't really affect this solution at all, nor do we really focus on the water with that. Okay, so that's just basically how it would approach problems like that. Now, we're looking at the pH of an acid. Okay, now let's take a look at an example, and instead we're going to be of making just some kind of salt in there. Now we're going to be adding a base, and this is a strong base, isn't it? Because we have sodium hydroxide. So we're going to have to do this in a couple of steps, because we have to first of all see what happens when I add the hydroxide in. Again, my major species. In this case, if we're going to be, and the reason we're listing this is to really keep track of everything and make sure we're accounting for it all. So in this case, we have the acetic acid. We're going to have the water because it's going to be dissociating in there. Remember, he doesn't really do much in there. We have the sodium ions from the sodium hydroxide. They don't do much, but I do have my acetate, C2H3O2. Okay, so that's from my acetic acid. That's this part. We have the hydrogen ions, and we also have now my hydroxide ions. That comes from here. All right, so those are all the major species in this, and we're going to account for these one at a time here. Now, first of all, let's take a look at the acetic acid and C2H3O2, and we know that we're going to be neutralizing that acetic acid with the hydroxide that's present. Okay, the question is how much. So from this, we're going to be pulling off one of the hydrogens, and we're going to make water, and that will give me my C2H3O2. Okay, so I see that I started with a 0.5 molar solution of this. Okay, I saw that I had 0.010 moles of my hydroxide. Okay, now what's going to happen? I'm going to end up with a 0.5 molar on this side as well, and notice that I'm going to be pulling off, so this is my initial, and I know it's 0.5 because that's what we started with on this side, okay? But I'm going to be using up 0.01, so my change is going to be a minus 0.01, a minus 0.01, and my acetate is going to gain that 0.01, isn't it? Okay, so there's my change that's going to be happening. Now at equilibrium, then I would have a 0.49. This would be 0, and this would be ending up being a 0.51 acetate that's freed up. Okay, now that's step 1, is to find the equilibrium of that base as we added. Now let's take a look at step 2 of this. Okay, step 2 is going to be to find the pH. The first step is going to be the equilibrium due to the base. Okay, this is a weak acid and a strong base. That's what we did. So let's take a look now. C2H3O2, that's going to dissociate into my hydrogen ions and my acetate, C2H3O2. And we saw that this was at equilibrium a 0.49, and it's going to lose a certain amount. And this guy's going to gain, and this guy is a 0.51 plus that X. Okay, and so at the end of things, I see my Ka. Again, I looked this value up. 1.8 times 10 to negative 5 is the Ka for acetic acid. That's going to equal X from my hydrogen times my 0.51 plus my X. Okay, that's from the acetate itself, and then the acetic acid was a 0.49 minus X. Okay, and so I end up canceling out my X's, and so I see 0.51, multiply both sides by 0.49, then divide by the 0.51. I end up with my, let's see, my X ends up being 1.75. 1.7 times 10 to negative 5, excuse me. And so if I plug that in, that my pH is the negative log of that, my pH ends up being 4.76. Okay, and so again, we do a weak acid, strong base equilibrium, and then we account for that change when we solve for this. So it's not really a buffer along the way by its traditional sense. It's going to be a weak acid, strong base, and then it goes and we see what happens from there. Now, let's take a look at example 4. That'll wrap up this section. We have 500 milliliters of this of the HCOOH, and we're going to be adding in 0.1 molar solution of sodium with the COOH. Okay, so the sodium, remember, that is going to be a non-factor here, but this is going to eat up some of the hydrogens that are going to be produced here. And so my major species are going to end up being that acid. We see the sodium in there, but they don't really do much. And I see the ion. Okay, those are the species that we get with this. Okay, so the first part, we're going to be taking a look at this, and we see that we have my acid is going to dissociate into the hydrogen ions and the COOH. And we started with a 0.25 molar solution. And let's see, we have, let's see, it's going to be losing, and so this is going to gain. And now we see I have a 0.1 molar solution of this ionic compound. So he's going to be sucking up or absorbing some of those hydrogens. Okay, and so if I take a look, we were given my Ka value for this. So my Ka ended up being a 1.8 times 10 to the negative 4. That equals X times my 0.1 plus X over my 0.25 minus X. Okay, my X ends up being 4.5 times 10 to the negative 4, and pH is the negative log of that value, and so I ended up with a 3.4 pH. Okay, and so remember, this is a small value here, so we disregard. I multiply both sides by 0.25, and that's how I ended up with this value. All right, so that's how we do that particular problem. Now, that's with some kind of buffer in there. Now, we're going to take that solution, and we're going to add to it 10 milliliters. Okay, so this is going to be making it a little bit more complex, and it's of a strong base. All right, so a couple things that we want to be tracking with this. All right, So let's go back. I see we have my acid, and my strong base is what we have to account for first. That's going to be making my water. So remember, this is going to be taking some of the hydrogens, isn't it? And so then we'll end up with some. It'll also dissociate and produce some of the ion. Okay, so we had a 0.125 mole solution. Okay, and or we had a 0.125 moles of this. Okay, and the reason we saw this is we had to account for the different values of, or the different amounts. So let's take a look at how I got that number first. We have the HCOOH. We had a 0.250 moles to begin with. Okay, we had a 0.250 moles per liter to begin with. Okay, now with this, we see that we have 500 milliliters worth. So if I have 500 milliliters worth, we have a 0.5 liters. Okay, so that gives me a 0.125 moles. Okay, now let's look at my sodium hydroxide. Okay, we had a 6 moles per liter. Okay, because it's a 6 molar solution. We have 6 moles per liter, but I only added 10 milliliters, which is 0.01 liters. And so how many moles are present? 0.06 moles of my sodium hydroxide. And remember, we also have this, okay? We saw that we have, within that, we had a 0.1 mole per liter, and we have 0.5 liters worth again. And so we see that we have 0.05 moles to work with here. Okay, so now we know all of our values along the way. How much of my hydroxide did we have? We had 0.06. Okay, and then looking on this side, because we're producing this, we ended up with 0.05 moles of my acetate along the way. Okay, now I'm going to be absorbing, using up all, is probably a better way to describe it, using up all my hydroxide, and that's going to be my change. And so at equilibrium, I end up with a value of 0.065 moles. This is 0, and this ends up being 0.11 moles. Okay, remember this is a 0.06. Okay, now be careful, because this is not my molarity, is it? It's just saying how many moles I have in here. Remember, I added 10 milliliters. So what's my total volume? My total volume is a 0.51 liters total. And so I end up with a 0.128 molar solution. On this side, I have 0.11 moles over 0.51 liters total. And so that gives me a 0.216 molar solution. Okay, so now I know at equilibrium how much I have of each of these. So let's put that in, and we see my HCOOH, we've accounted for the sodium hydroxide. Now whatever's left over, this guy's going to dissociate into the hydrogen ion and the COOH. Okay, so that's going to dissociate. I started with a 0.128, and it's going to lose a certain amount. It'll produce that many hydrogen ions, and this guy started at a 0.216 molar solution. He'll be gaining or eating up some of those hydrogen ions too. All right, so my Ka ends up being a 1.8 times 10 to the negative 4. That equals X for my hydrogen times my 0.216 plus my X over 0.128 minus X. Okay, and this is a small value. I can disregard those, multiply both sides by 0.128, and divide by my 0.216. My X ends up being 1.1 times 10 to the negative 4. Okay, now pH is going to be the negative log of that. I end up with a pH of 3.96. Okay, so what did we do in all of this? We had to first of all account for the different volumes. Okay, second of all, we ran that into our equilibrium to find out how much of my base, my strong base, was using up the acid properties, making sure we accounted for the total volume of everything that's in there. And then we were able to take the remaining at equilibrium, how much of my acid and how much of my ion was left over at the end of it. Okay, that's going to be it for this particular section. I think after this, you're going to be finding these get not too bad. Just kind of keep track of those things along the way.